Hello everyone, thanks for joining us today. My name is Ahmed M. Elkholy. I am excited to present our research paper entitled Comprehensive Study of the Impact of Unbalanced Loading in Power Losses and Voltage Quality in Distribution System. Authors are, except me, Dmitry Ivanovich Panfilov, Mikhail G. Astashev, and Andrei Sergeyevich Chasov. To begin, let's discuss the core aspect of distribution system. As the last stage of transmission process, distribution systems are responsible for delivering electrical energy to consumer. However, distribution systems are often fragile due to long distance, asymmetrical connections, and unsymmetrical loads. This issue adversely affects the operation, quality, and reliability of the power supplied. One of the primary challenges facing the distribution system is unbalanced operation or unsymmetrical loading, which leads to power and voltage instability, posing significant risks to both continuity and the economic aspect of power delivery. The major hurdle uh, here is the lack of an effective simulation platform and the automated tools to address asymmetrical loading. So in our study, we introduce simulation platform for distribution system using unified distribution system uh, distribution system modeling and an assisted management algorithm to control unbalancing condition using unified power control. Our agenda for today is unified power flow controllers, methodology and modeling, case study results, and conclusion. Let's start with unified power controller. Unsymmetrical component is a crucial tool for analyzing and managing the three-phase currents in the distribution system. By converting these phases into positive negative zero sequences, uh, the controllers can control and manage the angle uh, and phases uh, for the three-phase current using transformer coefficient. This relationship is mathematically represented as shown in the slide, where the three-phase current are transformed into symmetrical components. In three-wire system, UBC three-wire system is utilized to to utilizes two transformers with controllable coefficient and reactive element placed between them. The primary winding are connected to power line, while the secondary winding are connected in series with the reactive element. This configuration helps to management power flow effectively. While four wire while in four-wire system, UBC four-wire consists of two units: the power control unit and reactive control unit. The reactive control unit use the power control unit uses consistent transformer coefficient and reactive element to controlled by thyristor to control the power between the three phases, while the reactive control unit, on the other hand, using the same technology but to compensate the reactive power in the three phase. Carson equation. Let's moving to methodology. Carson equation are very important tool for modeling distribution system transmission line. Using image theory, these equations calculate the impedance between the overhead conductors and the earth. This involves defining the transmission line geometry, constructing a matrix, and applying a Carson equation for accurate impedance calculation. And this is a small flow chart that managing us to effectively determine the uh, impedance between the three phase and the earth. Started by defining the voltage level and then calculate the transmission line current, and then choose the conductor from the standard systems, and then identify the spacing between the conductor and then calculate the Z matrix. And Z matrix is calculating using this sample equation, in fact, that managing us to calculate the impedance matrix, and the other equations can be found in the paper. Newton-Raphson, on the other hand, is a method widely used for power flow studies, providing the basics for more advanced stability and reliability analysis. In our study, this method used to evaluate the effectiveness of the UBC in unbalanced distribution system. Uh, the main algorithm involved calculating the power flow, power losses, unbalanced coefficient, and transmission line efficiency, and varying in under varying load conditions. Assessing unsymmetrical loading involves calculating the voltage imbalance defined as the total departure from the nominal voltage. The imbalancing coefficient is the ratio between the positive and negative symmetrical component. According to IEEE standard 1159 for the year 2019, this coefficient must not exceed 1.5%, and the equation how to calculate the unbalanced ratio is presented here. Our case study is standard IEEE 4-bus system, but it is modified to match the Russian standard. This involved upscaling the transformer from 6 megavolt ampere to 8 megavolt ampere and changing the voltage level from 4.16 kilovolt to 10 kilovolt. We then conducting a cable sizing study to determine the new parameter, as shown as a Kerson equation section. The impedance matrix of the transmission line is calculating according to this parameter, voltage and current, and the specification of the conductors, GMR resistance, material stranding, and capacity. And here, a table shows the impedance matrix for the transmission line in our modified system. This value were obtained using Carson equation and are essential for conducting load flow studies. Table here presents the load data for IEEE 4-bus modified system, and the load flow results shown in the second table indicates the phase, magnitude, and angle at different buses under the given load and conditions. Let's discuss the results. In our study, we divide our results into two groups: the impact of the reactive power compensation and the power factor on the distribution system. The first group differentiate scenario based on the reactive power, while the second group examines the system response at different power factor values. Scenario description. The first scenario is balancing the three phase without any reactive power compensation, while the second scenario is compensating the reactive power only in the phase A, and third is the compensated reactive power in all phases, while the last one is not only compensating in all phases but also compensating in the transmission line. And this is the table shows how the reactive power is different from each scenario. Efficiency. This figure shows the efficiency of the transmission line against the variation in power of the phase on power of the phase A. As indicated, the efficiency is highest when the power in all phases is balanced. The second scenario starts with lower efficiency due to the removal of the reactive power in phase A. Unbalancing coefficient versus phase A power ratio is shown here. Voltage quality is significantly impacted by single phase reactive power compensation, with the balancing point shifted as the phase A power increases. The unbalancing coefficient decreases when the negative sequence decreases. In scenario 2, partial reactive power compensation reduces power losses but deteriorates the voltage quality and stability. The best effect is achieved through comprehensive reactive power compensation. This figure shows the neutral line losses against the phases of the phase A power ratio. As expected, lower losses increases with deviation from the balanced point. These combined losses of the three phases and the neutral line are also shown. This figure illustrates the power losses for the three phases against the phase A power ratio. The red shaded area indicates a significant reduction in power losses with reactive power compensation. The gray shaded area demonstrates the increased stability of the with reactive power compensation. This figure shows the combined power losses for the four losses. It confirming UBC reduces the power losses and improving the stability and the voltage quality with reactive power compensation. Power factor results. Here we present the results when the power factor is changing from 0.7 to 1, creating scenario 5, 6, 7, 8, 0.7, 0.8, 0.9, and 1, which we can show here enhancing power factor, reducing the power loss and decreasing the unbalancing coefficient. That means improving the overall system performance. In a conclusion, we introduce a power electronic device and to address asymmetrical load. Our assessment, including the efficiency of the transmission line and balancing coefficient, power losses, we modeled a Russian compatible distribution system using a standard cable and developed an electrical model using Carson equation. Our framework incorporated Newton-Raphson load flow equations with Carson equation and IEEE standards. The results show significant performance enhancement, addressing both stability and economic issues. Thank you for attention. We appreciate your interest in our research. If you have any question, please feel free to ask.